Welcome to Study Loop.
Hi there. So for this problem, we need to find the magnitude of the force that the magnetic field exerts on a ring if this ring carries some current of 4.6 milliamperes. So we are given the information of the radius of the wire ring. We are also given the magnitude of the magnetic field and its direction makes an angle of 20 degrees with a normal to the plane of the ring. So with that in mind, we can start by considering an infinitesimal segment of the loop. I'm gonna put that segment in here, just a tiny segment that we are going to call it ds. And the magnetic field is perpendicular to that segment, as you can see from the figure. And so the magnetic force on it has a magnitude that is going to be like the differential in force is going to be equal to the product between the current times the magnitude of the magnetic field times that tiny differential of the segment of the loop. Now, the horizontal component of this force has a magnitude of the following. I'm going to call it dFH for horizontal. So it's going to be the magnitude of the force of the differential force times the cosine of theta, because this will give us the horizontal component times the ds. However, this points inward toward the center of the loop. And also we will have a vertical component that has a magnitude of, we are going to call this Fy, and has a magnitude of EP sine of theta ds. Now, and as you can see from the figure, that force is going to point upward. Now, when we sum the forces on all of the segments of the loop, the horizontal component of the total force vanishes, since each segment of the wire can be paired with another that is diametrically opposed segment. So if we just took another segment diametrically opposed in here, so this is another ds, we can see that this force cancel with this force, and that will happen with another segment, one in here and one in here. So those forces cancel, so we can see that the net force that is experienced this um, wire ring and will have no contributions from the horizontal force. And however, the vertical component of the force do contribute to that net force. So what we need to do now, since we have a differential, is to integrate that, so that when we integrate this, the y component of the force, that is the only one that is contributing, is the current times the magnetic field times the sine of theta and the ds, or the segment, the tiny segment that we choose. So now in here we can see that all of this is a constant, so we can take it out of the integral. So we will have um, sine of theta. Remember that theta is also an information given for this problem. It is 20 degrees. So we will have the integral over all of these tiny segments on the ring. If you sum all of these tiny segments, you will obtain the circumference of this wire ring. So it will be, we know that the circumference of circular loop is 2 pi r, where r is the radius of the loop. So we have all of this information. So we need just simply to substitute all of these values. We have that the current is 4.6 milliamperes, amperes. So milli means 10 to the minus 3. So will this. And also we need to change that for the magnitude of the magnetic field so that it will be Tesla. And centimeters, we need to convert that to meters. So that will be to divide this number by 100. So that will give us 0.018 meters. Now with that set, we just simply substitute the values in here for 0.6 times 10 to the minus 3 amperes. The magnitude of the magnetic field is 3.4 times 10 to the minus 3 Tesla. The sine of 20 degrees, 2 times pi, and the radius, which is 0.018 meters. If we plot all of these values into the calculator, we obtain a value of 6 times 10 to the minus 7 newtons. And this is the force exerted by the magnetic field on the ring. Thank you.